Welcome folks, a video today on properties of dimensions. So last time we saw that the dimension of a vector space is the number of elements in the basis. So today we'll see some properties of that dimension, including the Goldilocks theorem, some properties of dimensions of ranks and transposes, and then we'll close with a dimension of the four subspaces. We now know that those four subsets from the end of our chapter on matrices are actually subspaces. Okay, so here's the first theorem. This theorem is, suppose that you have a vector space and a linearly independent set of vectors. Now, we'll also suppose W is a vector outside of the span of that set of linearly independent vectors. Then this new set, S prime, that's the set of linearly independent vectors plus W, ends up being linearly independent. So the proof of this is pretty cool, and it just goes back to the definition of linear independence. So we use a proof by contradiction. We suppose toward the contradiction that this set S prime is linearly dependent. Okay, if this set S prime is linearly dependent, then there must be a non-trivial relation of dependence on S prime. So let's write down that non-trivial relation of dependence. So a non-trivial relation of dependence on S prime has form alpha 1 V1 plus alpha 2 V2 all the way out to alpha T Vt plus beta W equals 0. Now remember, what makes this non-trivial is that not all of those coefficients can be 0. Okay, so at least one of those coefficients must be 0. So we'll break that statement down into two cases. In one case, we'll assume beta is 0. Well, if beta is 0, then we have what ends up being a non-trivial relation of dependence on the set S. Of course, since S is linearly independent, this is a contradiction. Now, on the other hand, if beta is not 0, well, then we can write one vector as a linear combination of the others, and we see that therefore the set is linearly dependent. Okay, of course, if W is minus 1 over beta alpha 1 V1 minus 1 over beta alpha 2 V2 and so on and so forth, then W is in the span of the set S, and this is a contradiction also. So the take-home message here is that whenever we add an element outside the span of a linearly independent set to another set, that new set is linearly independent. Okay, we'll end up using that theorem to prove this Goldilocks theorem. The Goldilocks theorem says, suppose that V is a vector space of dimension T, and S is a set of M vectors from V. Okay, so the following results apply. 1, if M is greater than T, then S is linearly dependent. Okay, of course, this follows from section D, right? More vectors than needed to span is linearly dependent. If M is less than T, then it turns out S does not span V. So we prove this by a contradiction. So if we suppose that S spans V, then S spans V, and the span of a basis is also V, but a basis has more vectors than in the basis than in the set S, which is a contradiction. Okay, points 3 and 4 also follow via contradiction by, in 3, assuming that S doesn't span V, and in 4 by assuming that S is linearly dependent. Okay, so a take-home message here is that when you know the dimension of a vector space, you only need to show either that a set with the right number of vectors spans a vector space or is linearly independent to show that it's a basis. So usually what one does is show that a set with the correct number of vectors is linearly independent, which implies that it spans a space and is therefore a basis. Okay, so typically it's a little less annoying to show that a set is linearly independent than to show that a set spans a space. So here's an example. We previously claimed that a basis for Pn is this set of polynomials 1x, x squared, all the way out to x to the n power. Now, since we know that the dimension of this polynomial set is n plus 1, all we have to do to show that C is a basis is to show that it's linearly independent. So let's go ahead and have a look at a relation of linear dependence on the set C. So that relation of linear dependence on the set C has form alpha 1 times 1 plus alpha 2 times 1 plus x plus alpha 3 times 1 plus x squared, and so on and so forth out to the last one equals to 0. So of course we can rearrange this, and when we rearrange this, it has a slightly different but a simpler form. So here's that form, and we've just sort of collected up our coefficients in terms of x to the power n rather than in terms of alphas. Okay, so we can see right away that alpha n plus 1 has to be 0, and if alpha n plus 1 is 0, alpha n is 0, and if alpha n is 0, alpha n minus 1 is 0, and so on and so forth, all the way down to alpha 1. We see, therefore, that the only relation of linear dependence on the set C is trivial. C is linearly independent, hence a basis for Pn. Here's another example. We previously showed that that this set B is a basis for the subspace Z of M22 given by these two conditions. And I'll go ahead and have you just construct another basis. Again, a basis for this subspace should have the same number of elements, 2, and all you have to do is show that they're both elements of the subspace and that they're both linearly independent. So check that out on the worksheet and let me know if you have some questions. Here's another example. We previously saw a basis of this subset of quartic polynomials where polynomial evaluation at 2 gives 0. So it's pretty quick to construct another. So here's another, the set x minus 2, x times x minus 2, x squared times x minus 2, and x squared times x minus 2 squared is a subset of W that is linearly independent. Hence, it's a basis. Okay, let's suppose that U and V are subspaces of W such that U is a proper subset of W. Then it turns out that the dimension of U is less than the dimension of V. Just a quick comment. It's a little more common to write a proper subset in this fashion, but in any case, they mean the same thing. So, so there are elements in V that are not elements in U, right? So it's sort of like strictly less than for sets. Okay, so here's a proof. We suppose that dimension of U is T, and that the dimension of V is M. Of course, then those two have bases with T and M elements respectively. We'll assume toward the contradiction that that the dimension of U is greater than or equal to the dimension of V. So if T, which is the dimension of BU, is greater than M, then it turns out that BU is linearly dependent by Goldilocks theorem, which contradicts its being a basis. Of course, if T is equal to M, then the span of BU is equal to U, which is also equal to V, which is a contradiction of U being a proper subset of V. So we see, therefore, that it must be that T is less than M. On the other hand, if U is a proper subset of V and the dimension of U is equal to the dimension of V, it must be that U is equal to V. And the proof of this is pretty straightforward. If U is a subset of V, then either U is a proper subset of V or U is equal to V. Of course, if U is a proper subset of V, then the dimension of U must be smaller than the dimension of V. So this case is out. It must be, therefore, that U is equal to V. Okay, so let's talk about ranks and transposes a little bit. For this matrix A, associated with archetype I, we know that the rank is the dimension of the column space of A. Okay, so since the reduced row echelon form of A has 3 non-zero rows, we know that the rank of A is equal to 3. Okay, so essentially here we've just applied theorem BCS to the matrix A. Now we can also find the rank of the transpose, right? And the rank of the transpose we can find just by row reducing the transpose. So here's the row reduced echelon form of the transpose. We see it has 3 non-zero rows, so the rank of the transpose is also 3. Okay, so this is sort of remarkable that the rank of the transpose and the rank of the matrix are the same, because the dimension of the column space, in this case 3, the column space is a subset of C4, and the column space of the transpose is a subset of C7, right? But these both have the same dimension. That turns out to always be true. This is a pretty cool theorem. So the proof of the theorem is that we suppose that A is m by n, then it turns out the rank of A is equal to the rank of the transpose. Now we know the rank of A is the dimension of the column space of A, and we know that it's that number R, which is the number of non-zero rows in its reduced row echelon form. Now, however, by theorem BRS, we know that this is also equal to the dimension of the row space of A. Of course, the dimension of the row space of A is exactly equal to the dimension of the column space of A transpose, which is the rank of the transpose. Okay, so this is rather surprising, right? The column space of A is a subset of Cm. The column space of A transpose is a subset of Cn. Those are totally different creatures altogether, but they have the same dimension. It's pretty cool. Okay. All right, so let's talk about the dimension of the 4 subsets, and this is all pretty quick. I'll have you prove this, in fact, on the theorem. Prove this theorem on the worksheet. So we'll start with the dimension of the column space of A, which is R. We know the dimension of the row space of A is also R, because that's the dimension of A transpose. On the other hand, the fact that the rank and the nullity add to the number of columns in the matrix tells us that the dimension of the null space is n minus R, and the dimension of the left null space, or the dimension of the null space of the transpose, is m minus R. So go ahead and check that proof out on the worksheet, and we can talk about it in class if you have questions. All right, folks, have a great day. We'll see you next time. So long for now.